Hey look, it's time for an update. So if you missed my previous video, this is a PTP clock showing PTP time on my network. This is an NTP clock showing NTP time on my network. And this is a GPS clock showing time straight from a GPS, a constellation of GPS satellites. So now I can finally compare if my GPS time is propagating through my network, through my time server, to these other clocks correctly. And if you look closely, you'll notice that the seconds are ticking, well, at least within a few microseconds of each other. I don't know if we're down to the nanosecond level yet on everything, but I will show you what's going on. This is a Switchberry. It's a custom 5-port PTP and Sync E network switch that has a Raspberry Pi CM4 inside and a configurable managed switch that you can set as a boundary clock or a transparent clock. If you don't know what these things mean, don't worry. Someday I will finally finish my PTP video and explain all this stuff. But this is a cool thing because it also has this little guy coming out that goes down there and over there to that little GPS distribution box back there. And it takes in GPS time, which is extremely accurate, probably more accurate than any other clock that you'll ever own in your life. And then it distributes that time through PTP and NTP over the network. This is one of my 2 time servers that I'm running right now. And down here, this is the other of the 2 time servers I'm running right now. And this one also has GPS. There's an itty bitty little pigtail back here that goes over to this GPS time distribution box. And this box has an input that comes straight from the antenna outside the building. And this is another NTP clock, but this is also outputting PTP time over the network through this little Intel NIC. I do not like Intel's NICs for timing. Not very fun. The drivers specifically have been challenging. And I have all the clocks now. Well, hold on. I have all the clocks now, including this one that is using Apple's time servers or maybe GPS. I don't know what the Apple Watch actually uses officially, but they're all ticking at the exact same time, which is something that's very fun to have because for months, actually for over a year now, I have not had all my clocks ticking at the same time because of various issues, most notably this little Intel network controller. It was super annoying. You can see my last video for what was going on with it. But up here on my monitor, I have my Mac now getting its time from time01.mmoffice.net. That is this Switchberry down here. So now I can check the accuracy for NTP between the 2 clocks, and they're within like 100 microseconds usually, which is pretty good. I think you could get that down better depending on the networking that you have in your studio. Like I have a lot of devices and a lot of traffic. I could probably isolate things better and get that down with NTP, but 100 microseconds isn't anything to sniff at. But PTP, that is the reason why I have this clock set up. PTP is set up so that I have 2 what are called grandmaster clocks, this one and the one back there. And using specialized packets, it can actually get much more accurate, down to nanoseconds. And if I look at the Switchberry's dashboard here, we can see that it is running PTP, multicast setup, and here's all the logs for it. This is a nice little dashboard. Some of the software is still a little bit of a work in progress, but it's gotten much more stable, and now this server can serve up PTP and NTP and take in time sources from anywhere. There's all these different SMA ports on the back which are configurable, so you can test and verify that your time is correct, or use external timing references for even more accurate time. Like let's say you are one of those crazy people that has atomic clocks. You could feed an atomic clock into here for even more accuracy. Anyway, this is all running, and these settings here, this is the settings for the one in the rack room back there. These settings have taken me weeks to nail down correctly because documentation is all over the board. Some things are only documented like in white papers or in blog posts or in random spots inside of like a product brochure. Like the values for time sources and clock accuracy and all that kind of stuff, it's not really documented in the PTP for Linux stuff anywhere. So some of it I would use Google's whatever their built-in AI thing is and kind of pester it until it found me a good reference. And then I'd go read a white paper and I'd be like, oh, there's a table of the actual values that this can be. Otherwise, you're sitting there just like re-implementing PTP from scratch and trying to figure out what hexadecimal fields store the information. An invaluable tool for that process is Wireshark. Wireshark can read all the packets going across your network, and I'm probably going to black this part out so you don't see all those, but I can narrow it down to PTP, and now you're just seeing PTP messages. So there's, with this two-step PTP that I'm using, there's announce, and then sync, and then follow up. And PTP uses those three sets of messages to give it like what kind of information can be passed, what's the actual time, and then how long has it been since the last packet, so you can really accurately measure that. And I'm going to stop here. I'm going to stop the feed so I don't flood my network here. But if I look at a message, you can dig into the actual stuff that's going on inside the PTP packet. So this is one of the clocks. And if I go to flags, it has all this information. So this was some of the stuff that I had to figure out, like how do I set these things? Where do I get them from when I'm displaying time? And how do I know if the clock is giving me TAI time, which is time without leap seconds, or UTC time, which is time with leap seconds? And how do I set it so that if it's giving TAI time, how do I know, like how do I tell clocks, hey, this is TAI and here's the leap seconds? So I figured out I had to set this origin current UTC offset is 37 seconds. I had to tell it that the UTC time is reasonable, like that's correct. I had to tell it it's using the PTP time scale, that means it's TAI time, and that time is traceable, meaning that I have traceable time back to a source, in this case GPS. And then it's like there's so many layers to this. You also have the different flags, like the clock class is 6. I don't even remember where I found that, like how to set that, but that's what it is for this one. If you know in the comments if there's a really good reference for all these values, let me know. But the other thing I had to figure out is how all this stuff works together. Like you get over here, GPS time comes in through this little SMA port, this antenna, and that needs to get out to the network, but you can't really just like shoot that out to here. You have to take that time and use PPS and the NMEA sentences, basically the things that tell what time it is and where you are with GPS. You have to use that to discipline the clock, and that is set through this TS2 PHC service. And here's the settings that I'm using for that. It's basically saying like here's the pin that the GPS timing will come into the NIC. That's that. And then I also am using a tool that Julian St. James created for splitting the GPS data, and that comes in through there. So you got the GPS timestamp and the GPS pulse per second coming into the network adapter. But then if you want NTP, you can't just use that out of the network adapter, at least not with like the current versions of NTP. There might be a way to do that in the future. You have to get the system time. So if you want the system time to be set too, then you need this thing called PHC2sys that takes the time off of the NIC and transfers it to the system clock. And then you have to give it some other settings, what the source is. So the source is the PTP device, the network interface. And then this was throwing me for a loop because some things have TAI time and other things have UTC and all that. Like the best thing to do is just to leave it like the defaults and then set it at the very end. So in here I tell it like take 30 seconds off, 37 seconds, which is the amount of leap seconds there are currently in existence according to the International Alliance of Clock People. And that makes it so that the time coming out of here and going into the system clock on the Raspberry Pi is correct. And then I can use that system clock to drive NTP, which I do up here in the Crony config. And I say the local clock, use that and call it Stratum 1. That means it's like, it's getting time from GPS. This is like the best time server you're gonna get for NTP. And I also had to disable all the other stuff in NTP and in Crony. Otherwise, it might use some of those, or it might screw up and not use the system clock correctly. So it's a whole thing. I wanted to make a quick update video on this stuff because I finally got those clocks in sync. And I feel like I should make a reference to the 90s, or I don't know if that was 2000s when NSYNC was hot. They're in sync, and that is great because now I can finally start to use these time testing tools like this Calnex Sentinel to actually measure how good my clocks are, or find out how many hundreds of nanoseconds or maybe even microseconds I'm off. And then I can do fun timing experiments after that, because I don't want to do the fun stuff in time until I know I have good time. And, in the end, once we get to the metaphysical level, we'll realize that time is just a construct anyway. And none of this really matters. I'm still working on a GPS video that I've been working on for over a year and a half. So someday I'll finish that too. I realized I'd gotten through this video and I never showed you what this actual board looks like. I think I showed a little bit of it in another video a while back, but this is the top case. In the bottom case, we're still kind of working on the design a little bit. Like one thing I'm trying today is putting a fan in here. There's a fan header over here, and the board does get a little toasty because there's no active cooling in here. But this board has a few important parts that if you want to buy one of these are expensive. They're not cheap, I'm not going to lie there. And yeah, if you know what this does, the price might not matter as much to you because there's not many things on the market like it. And for people that need it, they might need it. But anyway, this is the GNSS or GPS module. So this is the Neo M9N. This is not like the highest end chip for timing, but it's a good chip for GPS timing. And it has the antenna connection over here that connects up through here to that antenna port in the back. The rest of this board has these 4 SMAs that can be configured for pulse per second in, for pulse per second out, and for some other tasks when you're verifying your timing. And then it has mini HDMI or micro HDMI, USB 2.0, and a micro SD card for light compute modules. And over here there's the little debug or USB mini header for programming eMMC compute modules. Then there's a fan header. This is the chip that's one of the most important chips on here, the microchip. I forget what model this is exactly, but you might be able to see that. I can't see it through my viewfinder. But this is the chip that does the PTP timing, and you can set it to do boundary clock or transparent clock and all that kind of stuff through these ports. And the compute module 4, which is on the bottom over here, goes into that chip, its little LAN port. So this is kind of one thing that's on the chip here, and you can connect to it through your network that way. But on the bottom side, we have the compute module 4 is the main thing here, and you might notice some of the names down there. So it was fun to be part of this project, building this thing and testing it and building it and testing it. This is the 6th revision of this board. And each revision we've had some fun things, like this version. After working our way through all these other things, I realized like, oh, you can shut down the CM4. And then if you want to power it on, you have to turn on and off the whole switch. So, adding a power button. There's when you're doing hardware design, there's like a million things to optimize for. And finally, you get to some of the little usability things once you've fixed all the little bugs and quirks and things. Anyway, that's this board. Right now, I think a full kit with the case and the board and everything is like $1,000. So like I said, this is not something that I think that most home labbers are going to go out and buy. This is for people who are investigating timing and PTP specifically. This is not like a little switch that's going to compete with a $30 1 gigabit switch. But it's fully managed, timing aware, timing capable, and does synchronous Ethernet, Sync-E, so you can synchronize frequencies over Ethernet as well. So I'll be testing this more, and I will have, I'm working my way up to some other videos on this board and some other things with PTP, but we have a lot to work through before that. So anyway, yeah, level 2 Jeff, here's a little bonus bit where you get to see the board itself. Oh, and this slot, I didn't even mention it. This is for a Wi-Fi card. You could use it for other things too. It's PCI Express. But you could put a Wi-Fi 6E or Wi-Fi 7 card on here and run this as a Wi-Fi base station access point as well, or just to connect it wirelessly. Right now, I don't think there's any way to do PTP over Wi-Fi, but there are proposals, and I think the intention here is that eventually, if one of those proposals gets like traction, we could do PTP over Wi-Fi, which I don't see why there's any technical reason that's not possible. It might not get down to like the 5 nanosecond level, but I think we could do really well with Wi-Fi 6E and 7, and I guess Wi-Fi 8 when it comes out and whatever else. Anyway, that's it. See ya next time on Level 2 Jeff.